j'ai bien compris. Voilà. Et en tant qu'invité, nous avons aussi Dr Yang Xavier de EDF. Donc, je vous rappelle le contexte de la thèse chiffre et donc le contrat aussi avec EDF. Bien, vous avez environ 45 minutes pour présenter vos travaux de thèse, suite à quoi nous allons avoir un débat, un échange, questions-réponses par la suite. C'est à vous. Merci.
So, thank you very much, Madam President, for this introduction. And good morning and welcome, everyone, to my PhD thesis presentation. Before starting the presentation, I would like to thank all the other members of the jury committee for being here today. And I would like to start this presentation with a brief introduction and context of the subject of the use of direct current around its use for distribution systems. Then I would like to address the main upsides that were identified during this research concerning the use of DC for distribution systems and the main challenges associated to LVDC systems. And moving on, I would like to start the main part of this presentation, which will address three main subjects, which are the development and implementation of a main AC-DC converter responsible for deploying an LVDC distribution grid. Then moving on to the development of a protection methodology in order to protect people, the grid itself, and assets connected to the grid. And in the last part of the presentation, I would like to address the power quality domain from a DC perspective. And I will end this presentation recalling the main objectives and the main achievements and the contributions of this work, and I will talk a little bit about some perspective for the future steps of this research. So it is worth to start this presentation with a historical background, beginning at the end of the 19th century, where electricity was finding its way in order to become the most used way of transmitting and distributing energy all around the world. And a particular year in the same period, which is quite important, is the year of 1896, where the alternative current was battling DC current in order to be the most used one in order to transmit and distribute electricity, which ended in this year with the global adoption of alternative current systems, mainly due to the use of efficient AC transformers and the manufacturing of AC motors. And it was only in 1954 that we could see the first use of direct current for transmission systems that happened in Gotland in Sweden. And from this year on, mainly in the beginning of the 21st century, we can observe the use of direct current systems in more specific applications, but more globalized applications, such as shipboard applications or traction systems, or even data centers. And finally, it was only from 2010 and on that we were able to observe the use of DC in a more globalized form, and we also could observe the rising of different LVDC ecosystems all around the world, mainly in Europe and in China, but also in the United States. And to understand this global movement towards the use of DC for distribution systems, it is worth to look into this subject from two different perspectives. The first one concerning the energy generation side, in which we can observe an increasing presence of DC native loads in the energy mix, such as PV, photovoltaic panels, and batteries. And in the other side, in the other perspective, in the consumption side, we can see the same movement where we observe, once again, the exponential rising in DC native loads, mainly connected to electronics and IT devices, but also considering, for example, LED lighting and electric vehicle charging. And the third factor, which allows us to create an environment that could benefit from a DC link, meaning a direct current distribution grid, are the improvements in power electronic devices, but mainly in terms of efficiency increase and cost reduction. And this movement towards DC was something that was interesting for both of the industrial partners of this research, which are the R&D of EDF and NEDIS, which are co-funders of this work through the CIFRE convention. And from the industrial perspective, we were able to define a certain level, certain number of objectives, starting by the development of a cost-effective conversion structure, able to deploy an LVDC distribution grid, moving on to the development of a cost-effective, once again, selective protection scheme, and a third objective, which was the evaluation of power quality from a DC perspective. And each one of these objectives could then be classified into smaller objectives from a scientific point of view. And we could highlight, for example, when we are talking about power quality, it is worth to understanding which one of the topologies that exists is the best suited one for our application, which was mainly dedicated to residential and commercial buildings distribution systems. And if we are talking about protection, in a second place, it is worth to look into what types of protection plans we could use in order to maintain selectivity rules and in order to obtain a safe distribution systems in function of protection against electric shock and protection against a short circuit, for example. And third, in terms of power quality, it is worth to look into how can we define the main phenomena that impact an LVDC grid, how can we quantify and how can we qualify them. Then I would like to move on to the first step of this presentation, where I'm going to bring details of the main upsides that were identified through this research regarding LVDC systems. And the first one that is worth mentioning is a potential gain in terms of efficiency, because as you can see in the figure here, where I'm trying to compare an AC system, a classic AC system, to an LVDC distribution, we can see that since we have an AC-DC converter in the input of the grid, it allows us to mutualize a certain number of AC to DC conversion stages, which potentially can allow us to gain in efficiency. Moving on, the second upside that is worth mentioning regards controllability, because once again, the presence of the AC-DC converter in the input side of the grid allow us to regulate at the same time the DC voltage and the AC currents, which can help us to have a full control in terms of power exchange between the LV-AC and the LV-DC grid. And the final upside that is worth mentioning regards resiliency, because since in DC we do not need to synchronize different power generation sources in terms of frequency, we could exploit more complex grid topologies, such as the ring or the meshed grid topologies that you can see here in the picture, which could help us to improve the resiliency of the grid. Then, it is worth to mention that the LVDC system is still rising as a potential solution for distribution grids. And because of that, it still faces a certain number of challenges. And the first one that is worth mentioning regards protection. And in the protection domain, we could highlight three main challenges. The first one is the application of selectivity, because the presence of an input AC-DC converter, which often has a low short circuit power in its normal behavior and normal operation, it doesn't allow us to have proper margins in order to coordinate several protection devices in cascade in order to reach a selective protection scheme. Moving on, another protection problem and challenge is associated to the absence of RCD, residual current devices in DC, which are quite important to protect people from electric shock in TT grounding based distribution systems, such as the ones we have in France or in other countries around the world. And the third challenge that we can highlight is the difficulty around arc extinction, because if we compare this phenomena of arc extinction in AC, we can observe that we have a periodic zero crossing of the current, which do not naturally happen in DC, which at the end means that it's a lot harder to interrupt a fault in DC than in AC for protection devices. And the second challenge that is still holding back the global adoption of LVDC systems around the world is the evaluation of power quality in terms of transient phenomena, such as the ones that you can see represented here in the picture, such as voltage swells or voltage dips. And we still do not know how to characterize them in terms of voltage thresholds and in terms of time windows. And we can also look from the same perspective into steady state phenomena, such as the spectral disturbances, and all the evaluation and qualification of this type of phenomena is still to be done. And in our research, from our perspective, we are going to focus in the evaluation of some of these phenomena from the perspective of the behavior of the main AC-DC converter and how we can act into it in order to guarantee a certain level of compatibility. Then I would like to move on to the main part of this presentation, starting with the development and implementation of the main AC to DC interface converter. And when we are talking about power conversion topologies, it is worth to understand which are the ones that are available in the literature, for example, and which one is the best suited one for our application and for our scenario. And at a first, as a first analysis, we could classify these converter topologies into two great families. The first one being non-isolated converters, which do not have a dedicated transformer inside the conversion topology, such as the ones that I'm showing you here in the slide, such as the two-level voltage source converter or the neutral point clamp converter. Or we could even imagine more complex structures, such as the modular multi-level converter or even the Vienna rectifier if we are talking about unidirectional applications. And the second great family of power conversion topologies are the isolated converters, which often have a general representation, such as the one that I'm showing you in the, here in the picture. And in the last two DC to AC and AC to DC conversion stages, through the use of either a medium or high frequency transformer, we could imagine structures such as the single active bridge for unidirectional applications or the bidirectional bridge for bidirectional applications. And then, since for this research it is particularly interesting to understand the behavior of these conversion topologies during short circuit, since we are going to conduct an analysis related to protection schemes, it is worth once again to classify these conversion structures into two main families, which are the ones that behave passively during short circuit, meaning they do not have a means to act directly in order to stop or to limit short circuit currents. And in this family, we can find the two-level voltage source converter or the neutral point clamp converter, for example. And the second family, which is particularly interesting in this research, are the ones that can behave actively during short circuit, such as the modular multi-level converters when they are composed by submodules of full bridge or hybrid bridge structures. And we can also find in this family both of the isolated structures that I showed you in the previous slide, which are the single and the double active bridge. And for these reasons, we chose at the end to exploit a topology that is corresponds to an isolated converter, mainly to due to two main characteristics, which are the possibility of reaching high power density in this type of topology, mainly because of the use of a medium or high frequency transformer, in our case, a medium frequency transformer, because it is significantly small in terms of volume and in terms of mass. And the second and most important characteristic of this type of topology is that they are able to limit short circuit currents, which could help us at the end to coordinate its operation with other protection devices put in cascade downstream. In terms of each conversion step particularly, we are going to address the first rectifier stage from two different perspectives. In simulation, we are going to develop a bidirectional model where this stage is represented as a two-level voltage source converter. And for the real implementation, we decided to go for a simplified version using a unidirectional passive rectifier in the input stage. And for the last two conversion stages, the DC-AC and the AC-DC, once again, we decided to study them from two different perspectives, the same. In simulation, we developed a simulation model which is bidirectional, considering the double active bridge, which once again was simplified for the final implementation in a experimental prototype to be a single active bridge. Then here, what I would like to show you is the final bidirectional simulation model that was developed through this work, which was done using Plex platform. And this stage was mainly used to validate the modeling of the input rectifier, meaning the two-level voltage source converter. And following a certain number of designing rules, we were able to size the input filter in order for the reactors to limit the maximum THD to 5%. And the same similar reasoning was applied in order to develop and to implement the output capacitive filter. And for this scenario, we tried to limit the maximum voltage oscillation in the intermediary DC bus to 0.2 volts. And here you can see the final results of this stage of the research. And in blue, you can see the regulation of the intermediary DC bus voltage, for which we could achieve a 15 millisecond time response with a 20% overshoot. And if we execute a zoom in this figure, which represents the DC voltage, and in this figure representing the three-phase AC currents, we were able as well to validate the designing rules and to look if the values in terms of maximum THD and in terms of peak-to-peak voltage variation were respected. And indeed, we reach a maximum THD of 2.1% and a maximum peak-to-peak voltage variation of 0.15 volts. Here I would like to show you the evolution of the bidirectional model and the simplification of this model in order to serve as a base simulation model for the implementation of the real experimental prototype. And we can see here, apart from the changes in terms of unidirectionality, changing the VSC for a passive rectifier, we can see an improved model of the medium frequency transformer that was we were able to implement through real measurements executed using the real medium frequency transformer that was being implemented in parallel. We can see the same thing considering the output filters, where we were able to deploy a more improved version of this model. Once again, that was possible through experimental measurements done with the experimental prototype. And we also used a simplified version of the real voltage and current source, current sensors that were used once again in the experimental prototype. And in this slide, what I would like to show you is the final results in closed loop obtained through the use of the simulation model. in which in green you can see the regulation of the output DC voltage, where we were able to reach a 7 millisecond time response with essentially no overshoot. And it's worth mentioning that the curve that you can see here in blue concerns the output inductor current that is also regulated through the inner loop of the simulation model. And we can see that it has a faster dynamic, which is needed in our case in order to be able to limit short circuit currents at an acceptable time period. And then all this simulation model evolved to the implementation of a real prototype that I'm showing you here in the picture, that corresponds to, it was designed to operate in a maximum operation point of 3.5 kilowatt, corresponding to 350 volts and 10 amps. And in the picture, you can see the input block in one that is composed by the passive rectifier followed by the intermediary DC bus. You can see in 2 the active bridge composed by silicon carbide MOSFETs. In 3, you can see the simplified version of the medium frequency transformer that operates in the frequency of 40 kilohertz. In 4, you can see the passive bridge, once again made by silicon carbide semiconductors. In 5, you can see the output filter composed by the output inductor and a set of capacitors. And finally, in 6, you can see the DSP-based control, which is responsible for controlling the complete topology of the converter. And I would like to show you in this picture the final results that were obtained through the exploitation of our experimental converter prototype. And you can see here that for a maximum operation point of 230 volts with 8 amps corresponding to a maximum frequency of 1.9 kilowatt, we were able to reach an operation where the DC current and DC voltage were reasonably stable, which allowed us in a certain way to validate the execution and the implementation of our experimental prototype. And finally, I would like to show you a comparative slide where I'm comparing the results that were obtained here in the left side of the presentation using Plex simulation, and here it is a zoomed out version of the picture you just saw in the previous slide. And we can see once again that comparing both results, we reach in both cases a stable DC voltage, a triangular current in the output inductor, which is once again expected because we have at the output part of the converter a full wave rectifier followed by an LC filter. And another fact that allowed us to validate our simulation model was that for the same operation point, we used in the control system a 45% duty cycle in order to obtain this operation point. And once this stage regarding the development and implementation of the power converter prototype was finished, we could then move on and concentrate our focus in the development of the protection scheme. And before going into the intricacies of the protection scheme itself, it is worth to highlight what type of grid topology was the one that we focused during this work and during this research, which is the one that you can see here in the slide. And regarding its characteristics, it corresponds to a monopolar constant voltage of 350 volts with a single distribution bus using an isolated AC-DC transformer in the input side of an AC-DC converter in the input side of the grid. And once again, before going into the details of the protection scheme, it is worth to understand and to try to explain how the thermal endurance of the main AC-DC converter impacts the protection plan, the protection scheme. And in order to understand the thermal endurance, it is necessary to understand how temperature evolves in a power converter and how to model this type of evolution. And in terms of temperature evolution, it is in a power electronics converter, it is mainly due to two types of losses, which are conduction losses that you can see here, and in 1 and 3 you can see the commutation or switching losses, which could then be modeled as a heat flow that is passing through a set of impedances, which are the impedance from junction of the semiconductor to its case, the impedance between case and heatsink, and finally the impedance between heatsink and the air. And this set of impedances and heat flow generated by losses can be modeled in Plex platform, as you can see here in the picture. And for our research in particular, we focused our efforts into the modeling of the thermal circuit of the last passive bridge, because for our converter, the SiC diodes proved to be the weakest link in terms of thermal endurance. So here you can see the thermal model in Plex, and in order to validate this model, we executed similar operation points in experimental tests and in simulation in order to compare our results. And for a 10-minute simulation using 230 volts DC and 8 amps, we reached at the end a 70.5 K temperature in the SiC diodes, which were then compared to experimental tests, which were made with the use of a thermal camera. And as you can see here in the picture, the diode bridge and the diodes inside this bridge reach a maximum temperature of 73.5 degrees, which allowed us to validate its operation and to validate our simulation model. Then entering the real development and the real implementation of the protection scheme, it is worth to look look into this subject from two different perspectives. The first one is to study pole-to-pole faults, and our proposition for protecting the system from pole-to-pole faults is to use a set of ultra-fast fuses in the input side of the grid to protect the converter and the grid itself from short circuit, and to use thermomagnetic circuit breakers that you can see here to protect each load feeder or each other feeder that is connected directly to the distribution system. And here I present you the technique and the strategy that was used in this work in order to try to coordinate all these protection devices with the final objective of reaching a selective protection scheme. And the strategy used was to use inverse time over current curves, where the behavior of each one of the components of the grid could be modeled, such as the thermal behavior of the power electronic converter in red, in dark blue the behavior of the ultra-fast fuses, in light blue and in green the behavior of the circuit breakers. And then there is the other side and the other perspective of the protection scheme, which concerns the protection against pole-to-ground faults. And once again, we could classify pole-to-ground faults into two great families. The first one being the direct contacts, meaning when a user can touch and access an active part of the grid. And from our perspective, the best way to protect the system from direct contacts is to use class 2 equipment, meaning reinforced or double insulation for equipment and for the installation. And the second type of pole-to-ground faults concerns the indirect contacts that are often represented by insulation faults at equipment level. And from our perspective, once again, the best way to protect the system from it is to use a TNS earthing system, because with this earthing system, pole-to-ground faults behave similarly to pole-to-pole faults, meaning that we could use the same protection devices to protect the system from pole-to-pole faults here once again. And in order to increase the protection level of the protection scheme against pole-to-ground faults, we could also imagine a similar function to a residual current device operated by the main AC-DC converter, comparing, for example, the measurements of the positive and the negative pole in order to recreate this RCD function. And then I would like to show you the final protection architecture that was considered in this work, in which we added an AC protection device, an AC thermomagnetic circuit breaker associated with a 30 milliamps residual current device that was put here in the case in which the converter is not capable of protecting itself, and the fuses and the DC thermomagnetic circuit breakers do not operate correctly. So here you can see the set of protection devices that we were able to implement in order to conceive the complete protection architecture. And finally, what I would like to show you here was the final results that were obtained from our efforts in order to coordinate all these protection devices. And here you can see that since for a current of 60 amps, we have a selective point of operation, it is worth to choose this current level in order to be the saturation current for the current limitation techniques. As you can see here, the converter is able to saturate the current and to limit the current to a maximum level of operation of 60 amps, where we are selective, because between the behavior of the converter in blue, the behavior of the fuse, and the behavior of the circuit breakers in gray, we do not have crossing points. However, in the zone that is circled in red, we indeed have a crossing point, and the first crossing point that we can see here, it corresponds to an operation and to a short circuit as a consequence of 53 amps, meaning that for this operation zone circled in red, the converter must be capable of protecting itself. And in order to do that, we implemented a temporal function that is represented once again in this curve, where the converter limits the short circuit current for a certain time, that for us is defined to be 50 milliseconds, and then it completely shuts down the LVDC grid in order to avoid the SiC diodes to reach their maximum junction temperature, which is, for our case, 175 degrees. And then I would like to move on to the last part of the main course of this presentation, which concerns the evaluation of power quality indicators through a certain number of parameters and through a DC perspective. And it is worth to start this discussion talking about and comparing what indicators already exist in order to evaluate AC systems and how we could adapt these indicators in order to evaluate DC systems. And there are several indicators and parameters that could be used. One that is quite important for our research is the spectral disturbance one, because we are trying to assess and to address the subject of steady state phenomena in power quality. And in AC, this indicator is particularly evaluated through a set of parameters such as harmonics, or THD, or TWD. And in DC, a parallel analysis could be done in which we could use the concept of ripple, which consists of all the components in a DC voltage or current apart from the 0 Hertz component. And the ripple could once again be evaluated from different perspectives, such as peak-to-peak ripple, or RMS ripple, or even total distortion level. And once we defined the main parameters that could be used in order to evaluate power quality in a DC system, we focused our efforts in terms of transient analysis into two main indicators, which are voltage swells and voltage dips, that in DC are mainly caused by the connection or disconnection of loads. And we found out during our work that to prevent damage in equipment and to guard a certain level of compatibility with sources and loads, we could act in the control of the power converter in order to mitigate the influence of voltage swells and voltage dips, either from the AC side, coming from the AC side, or coming from the DC side. And we could evaluate the behavior of our converter using already existing curves, such as the ET curve, which was developed in order to maintain a certain level of compatibility with electronic equipment. And what I'm trying to show you here with these figures are the results that were obtained when our DC grid was submitted to AC voltage variations, voltage dips or voltage swells, and to DC voltage variations. And we can see here that even for a 25% AC voltage dip that largely impacts our intermediary DC bus voltage, as you can see here in blue, we can see that the output DC voltage in the output part of our converter is not very impacted, which means at the end that our control is capable of bringing the voltage back into acceptable time periods. And the same type of test was executed using load increase in order to create a voltage dip in DC. And once again, we can see that even for a 300% load increase, once again, that you can see here in orange, once again, our control is capable of bringing the voltage back into the rated voltage levels in acceptable time periods that were compared to the ones that we can find in the ETIC curve, for example. And following the same reasoning in terms of steady state phenomena, it was important, and it was one of the focus of this work, to understand how we could evaluate the behavior of our converter in terms of steady state power quality analysis, considering the concept of ripple as a principle, as a main indicator. And you can see here measurements that were executed using the experimental prototype, in which we were able to execute an spectral analysis, and through the spectral analysis to calculate the RMS ripple and the peak-to-peak ripple, where we reach a 0.39% voltage ripple in terms of RMS indicator, and a peak-to-peak ripple of 2.33%, which are quite reasonable results if compared to the ones that we can find in the literature for similar conversion topologies. And it is also worth mentioning that the spectral analysis that was executed allowed us to identify three main spectral components that are worth mentioning. The first one being the 300 Hertz component, and by far the most difficult one to filter, that comes from the input rectifier. The second one, it is the component at 80 kilohertz coming from the commutation of SiC MOSFETs in the active bridge. And the third one being the 810 kilohertz that are potentially generated by an interaction between the snubber capacitors in the active bridge and the parasitic inductance that are all over, that we can find all over the electric board and in the connections through the converter. And then the last aspect that I would like to address concerning power quality evaluation concerns the disturbance propagation through a distribution grid, and to understand what is the challenge in DC systems. It is worth, once again, to do a comparison to how this type of study is executed in AC. And in AC, we can represent, for this type of study, we can represent the AC distribution grid through a set of impedances, the first one being the impedance, low frequency impedance of the transformer, followed by the impedance of the grid, and the disturbances that are injected in the grid and in the point of common coupling by loads or a set of loads could be represented by a current source. And in DC, the problem is that we, instead of having an AC transformer, we have an AC-DC converter, which is quite more difficult to model in terms of frequency-dependent impedance. And our proposition and the method that we used in order to address this subject was to use either the model of the power electronic converter or the real converter prototype, and in cascade in the output of the converter to connect a source of current disturbances that could have different shapes, such as sinusoidal shapes if we are looking into frequency scanning methods, which have a higher precision, or squared or pulsed waves if we are looking into having a larger defined frequency-dependent model with only one experimental test. And here you can see the final results that were obtained through experimental tests, where you can see that we were able to create pulsed waves of disturbing current with a base frequency of 50 Hertz, which allowed us to obtain, through a spectral representation of voltage A current, a frequency-dependent impedance model that could vary from 0 to 2 kilohertz in terms of range. And this frequency impedance model allowed us to determine a first resonance point, which potentially corresponded to the frequency, to the resonance frequency that were obtained with real values measured with the output LC filter, which corresponded to a resonance frequency of 432 Hertz. And then I would like to end this presentation with recalling the main conclusions and main contributions of this work, which are, at first, the design and implementation of an AC-DC main interface converter responsible for managing the interface between the LVAC and LVDC grid using silicon carbide semiconductors. In second, the design of a selective protection scheme that were partially verified using simulation and experimental tests. In third place, the analysis of power quality assessment methods, quantification and qualification, using a DC, an LVDC perspective. And in terms of future steps, the first subject I would like to address is the possible evolutions in terms of the power converter prototype. And in the first place, you can see that the input rectifier could be changed, and we could focus in more complex structures that could bring us some benefits, such as the Vienna rectifier if we are looking into unidirectional applications, or the implementation of the two-level voltage source converter in terms of bidirectional applications. In two, we can see that we could improve the connections with the intermediary DC bus in order to reduce the parasitic inductances. In three, we could add resistors in the snubber circuit in order to mitigate high frequency disturbances. And in 4 and 5, we could also increase the levels of inductance and capacitance of the output filters in order to bring more stability to the grid. And finally, to implement, using the DSP controller, the closed loop regulation. Specifically in terms of protection scheme, what we think it would be interesting to do in future steps would be to execute experimental tests using the closed loop regulation in order to execute the current limitation technique and to validate its operation for our protection scheme, to consider the influence of long distance faults and how it impacts our protection scheme, and how we could maintain selectivity as well for this type of fault, to execute real experimental short circuit tests in order to validate our selective protection scheme, and maybe to compare, certainly to compare our results with other strategies that can be found in the literature, such as the ones that are using solid state circuit breakers. And in terms of power quality, we think it would be interesting to expand our analysis in terms of transient and steady state evaluation for more complex models, either more complex models of the grid and more complex models of converters, considering, for example, the presence of DC to DC converters associated to loads, and as well to expand the frequency range of our impedance model that were obtained for a range of 0 to 2 kilohertz. And this is a work that is already in progress. And the results that I'm showing here were obtained in the last parts of this PhD research, where we were able to obtain a 10 kilohertz base frequency current disturbance, which allowed us to improve our frequency dependent impedance model up to 150 kilohertz. So I would like to thank you very much for your attention, and if you have questions, I will be glad to try to answer them.
Thank you for your presentation. So now we have to have a debate and an exchange. So I invite firstly Professor Inigo Martinez de Alegria to make comments regarding your work and regarding your defense.
Thank you very much. If you want to ask questions either in English or in French, it's okay. It's as you prefer.
Thank you very much, Manuela, and thank you very much, Estia, for inviting me to this presentation. First of all, I would like to congratulate you, César. I have enjoyed reading your document. I think it's a high-quality document, and especially I have enjoyed a lot your presentation. I think it has been very clear, up to the point. It has allowed me to understand a few details in the document that you have explained much better. And also, you have been very tight in the time schedule, which is also important. But now I will do a few comments and a few questions on your work, okay?
Thank you very much.
Yes, the first thing is the selection of the topology. In the document, I lacked a little bit more of explanation that I have seen here, but however, I think that in your document, I have appreciated a little bit more of more in-depth comparison of the converters, because in the end, you have opted for a quite traditional converter. Okay, and my question is why not use converters that have a little bit better properties? I think, in my opinion, for this application, especially if we are using just I will say one quadrant converter, only power from the grid to the loads, not bidirectional converter. Why not use Vienna rectifier or something like that? Why have you chosen this topology? That would be my first question.
Okay, thank you very much for the very pertinent question. Indeed, I think we could have used more complex structures, such as the suggestions you just made, such as the Vienna rectifier. Our problem was mainly connected to the time of execution of the prototype itself, which was quite important for the two last steps of the PhD research, but were not the main focus of analysis. So we tried indeed to have a prototype as fast as possible in order to be able to use it to achieve conclusions regarding the protection scheme and the analysis of the power quality. But we see it just as you, as a possibility for future steps of this research, is to indeed think of more complex and better topologies, mainly for the input rectifier, such as the Vienna, or if we are talking about bidirectional applications, the two-level VSC, or even more complex structures.
Okay, thank you very much. That clears out the selection. That's the reason for my comment. I think in the document, even if experimentally you will build the more the more let's say conventional approach,
Mhm.
I think the document should have included a little bit more comment on the properties of the different converters, and saying what are the benefits or the best results, and then just explain. But we will use this kind for the time. Okay, and that
Thank you.
that is linked to another comment and question also, because when we go at the end of the presentation and look at the power quality issues,
Mhm.
there is a very significant 300 hertz component. 300 hertz is 6 times 50. That's the rectifier. That's the rectifier ripple, and that's why I consider that other type of rectifiers that help to reduce this ripple, that is the one that is more difficult to filter out, would have been better, and that's why that's the one of my main critics. It's not a real hard critic, okay, but why not mention this, that you can achieve better results, even theoretically. You can explain theoretically. You don't need to do the experiments.
Perfect.
Okay.
Thank you very much.
Let me see. Yeah, another question is, I understand that the converter, the SiC converter, the silicon carbide controller, is operating at 80 kilohertz. What frequency are you switching it? Because it's not very clear from.
It's operating in 40 kilohertz,
Okay,
but
42 times.
I think the little confusion is because of the spectral component, maybe. It's because it is rectified through a passive rectifier at the end. That's why we find an 80 kilohertz instead of a 40 kilohertz, but indeed it is operating in 40 kilohertz as a switching frequency.
Okay, so 80 is 2 times, right? Which is okay. Regarding the prototype, also from the photograph, I recommend that if you go to, I think, let me see, where's the photograph of the converter? I don't remember.
This one, maybe?
Yeah, this one. Yeah, 39, slide 39. Yeah, because you're using silicon carbide, high frequency switching, etc. In my opinion, this prototype is very good for an initial test, but switching, the most important thing you are going to find in these converters are switching problems. Okay, so and the wiring of this prototype is what I mentioned is that the wiring is not. You should use bus bars instead of wires, because
Copper
you
bus
improve
bars.
a lot the results, especially because you are evaluating power quality. And in this case, I think your work is a good work. It's very proper, but the results are a little bit difficult to use, because I'm not sure if the quality of the results are more involved because of the quality of the wiring, and maybe you could improve the results of the waveform qualities just by improving the bus bars of connection. Okay, so my proposal is that in the next step, if you continue with this, you don't have to change the whole prototype, but the wiring, it would be very important in order to reduce a lot of noise.
Perfect.
Okay, and then I have a couple of questions. First, I didn't mention, I totally agree with, I find the field of research you have chosen is very important. I totally agree with that there is more and more necessity for DC grids, especially for avoiding redundancy of power converters. But I have one question. In the main architecture, when you compare AC to DC, the main thing is that you use an AC to DC main converter in order to avoid a lot of small AC to DC converters in each load or device. Okay, have you made a study of the cost and efficiency of one option or the other? I don't know if you know, just a big converter versus a lot of small AC-DC converters. That's the main advantage, let's say. But have you at least made a thought about the cost and efficiency? And because I don't see data on this on the document.
there is indeed a great discussion around this subject in the literature, but most of the sources that I evaluated gave better results with the use of a central AC-DC converter, mainly when we are considering that there is local generation and local consumption, and for example, for commercial buildings, where we have the more and more IT technology loads connected to the grid. So we can find results, for example, of 11% or even 15% efficiency increase. But once again, it's a great discussion. I think it's only the beginning of discussion from a scientific point of view, because there are other sources that conclude the opposite, that consider smaller AC to DC conversion steps for equipment, for example, are better than using the main converter. But from my perspective, the first one, using the main converter, it's still worth it in terms of efficiency.
Okay, I kind of agree with your conclusion. And also I think it's not only that, but also the wiring, the power losses in the wiring, etc. I think when we go to DC, we have a lot of benefits. But it's true that it's still in discussion. And just I will finish with two very short questions. The first thing is, there is a lot of AC breakers, but DC breakers, it's harder to find. So what can you comment on this, just in general? What do you think it will be a limiting factor, or do you think the technology is reaching a stage where we will have DC breakers just as AC breakers?
I think there will be a time that we are going to have AC and DC breakers, with the DC breakers being completely able to operate correctly. But it is for now, in our period of time now, it is a great problem, a great challenge. Because, for example, what we can find with manufacturers is that for DC breakers, they are using AC breakers with a smaller voltage of operation. The technology hasn't yet evolved, but it is mainly due to a bidirectional relation, because manufacturers doesn't develop this type of technology because there are no standards. And because there are no standards, they do not develop this type of technology. So it's a little complicated, but I think that we were going to reach a time where we will have DC breakers, either solid state or thermomagnetic. It's still an open discussion.
Okay, and last, I also appreciate you built a medium frequency transformer for your prototype, which is, it's not easy to build medium frequency transformers that are efficient and work properly. And again, did you find difficulties in either finding or building yourself a medium frequency transformer?
Yeah, one of the main difficulties that we found was for the first model, because we made, I think we made 2 or 3 models of the medium frequency transformer, was that for the first one I used normal copper wires, and I experienced losses, huge losses, because I haven't yet found the knowledge, the information around the use of Leeds wires, which allowed me to increase the global efficiency of the transformer. And to find a proper magnetic core is also difficulty. In our case, we are using ferrite, but there are lots of different types of magnetic cores, such as amorphous and everything. It was also a little bit difficult to choose the best one to our application.
Okay, so I finish just by congratulating you for your work.
Thank you very much.
My only small critique is that I see a lack of a little bit more in-depth theoretical explanations in a few aspects, but other than that, congratulations for your work, and thank you, Manuela.
Thank you very much.
Bien, je passe en français. Donc là, je donne la parole au professeur Loïc Keval, deuxième rapporteur de la thèse.
Hi, César. Nice
Hi.
to meet you, finally.
Thank you very much.
So I was very happy to be invited to report on this. The main reason is that we are working on something very similar, as you know, with Frédéric. He's here.
Indeed.
He will defend on November 22nd, something like that. So you are welcome to come to see his defense, because you will see it's totally, it's a good complement. It's totally different approaches. So that's very interesting from that part. So I kind of discovered all your work through your report, and especially all the decisions that you had to make, but starting from the same problem. Okay, so I will start first by some general remarks about your report and presentation. I think it's very relevant for the community, and it's only a starting point. Okay, it's a difficult work because actually you don't have so much stuff about this kind of grid-connected converter. It's a lot of literature review. You have 266 references. It's a lot of work to read, summarize. It's a lot of work for us as reporter to read through. So the report is about 120 pages, and let's say 80 pages is kind of literature review. But in between, you have some very interesting insights, comments, and analysis in between. So it's kind of difficult to see what is a literature review and what is your originality inside. Okay, but it's there. You made a lot of pedagogical efforts, especially in some figures. For example, I really like the figure about short-circuit behavior of the full bridge MMC, which I'm going to use in my lectures from now on. Because it's nice to just draw it another way, just to show how it behaves during the short circuit. And I appreciated a lot all the difficult decisions you had to make with your supervision, so that you will be able to go towards a working prototype. We talked about the design of the medium frequency transformers. Even if you had 3 iterations, still the sizing, and like, let's say, numerical sizing, you put this on the side, we see it, because it's a lot of work. You wanted it to work, so we understand that. You made this choice to adopt diode bridge instead of 2-level voltage source converter, to use a SAB instead of a DAB, so that's a lot of decisions, but that makes it that you have a working prototype on the table, and that's already a good, very good challenge, okay, in 3 years. Actually, 3 years is super short. So well done for that. I totally understand from the experimental point of view, and I congratulate you, because it's nice to see it working.
Thank you.
Outside of this, a lot of work on simulation and experiment, as we can see here. Actually, from my point of view, after reading the thesis and thinking a lot, I think this is actually not the main contribution of this work. For me, but it's only my personal thinking. I think that the main contribution is actually really the discussion about this complex system, which will be the future DC grid, low voltage DC grid, and how we can make it work with all these protection problems, selectivity. This is, from my point of view, the real originality of the work, and that's a bit hidden inside the literature review here and there. And that's very difficult to sell. And I think here you make this presentation, you sell us, for example, this prototype, but it's so difficult to sell all this reflection about this future LVDC grid that still doesn't exist, and you have to interact with so many people to understand a bit. That's difficult to sell. So let's keep on working on this, but well done on this.
Thank you.
Okay, I have now some questions. It's actually not to challenge you or what, I have the same questions, okay? So maybe you can give me some response. So the first one was a comment that you already discussed about this. In your thesis, you stated, it was on page 36, energy saving is feasible through mutualization of multiple AC-DC conversion steps through a central converter. So you just discussed right now, and you say, okay, it's still in discussion. I agree. We should do more thesis about this. But a bit later, on page 50, you state, so it's a bit later after you choose a conversion, if a more powerful converter is able to withstand fault condition with higher short circuit current, meaning you are basically oversizing the converter, okay? So if I oversize the converter, it also will perform with a considerably lower efficiency under normal condition. Basically, since it's oversized, you are using it at partial loading, so you operate it with lower efficiency. So here we see that there is a big question. First you say, okay, I'm going to take all the converters from the user, put it in the substation. So I'm going to have a bigger one. But if you do that, this converter is not going to be oversized, but it's going to be used always, all the time at partial loading, of course. So it's going to have lower efficiency at the end. So what do you think?
I think that is a very pertinent discussion. Indeed, what I found in the literature, mainly in the beginning of the PhD thesis work, was that most part of the studies that talk about this subject do not consider this type of approach, meaning they consider a fixed efficiency for the main AC-DC converter, and they only look into the variable efficiency of converters associated to loads. And indeed, for the small number of studies that actually take into account the global efficiency and the variation of its efficiency in terms of point of operation, if we have a lot of loads connected or not, they actually find, when they find efficiency gains, they find quite smaller efficiency gains. So it's once again a very pertinent and still open discussion. But we could also discuss around the fact of oversizing the converter in order to be able to protect it, or use some other types of strategies or protection devices in order to...
That's another question.
Okay.
So basically to summarize, looks like there is more work to do on this.
Yeah,
just to know if we need this interface converter at the substation or something else. I totally agree. I have no idea if it's the best solution today. Okay, so in chapter 2, basically you are comparing many topologies, and you summarized it in your presentation today a bit better than in the manuscript. Maybe you chose this topology for two main reasons: high power density, and you say because I'm going to use a medium frequency transformer, which is better in terms of power density, okay, and current limitations, okay. So looks like this is your two main constraints. Why not? Let's discuss about the first one. I think you have slide 23.
Almost there.
Okay.
23.
This one is perfect. So this is basically the system that you are studying.
Mm-hmm.
And you said, I'm going to choose this topology because it has a high power medium frequency transformer. I agree. Why do you need a transformer inside the converter? You already have a transformer at the medium voltage, low voltage substation. Why do you need another one inside the converter?
It mainly depends on the type of earthing system that we have in the first side, in the input side of the AC to DC converter. And if we have a direct connection to the earth, we need to isolate it, to have a galvanic isolation in order to separate the earthing from the AC system and the earthing from the DC system. There are some studies that consider connected that consider connected groundings, but they experience some problems around electromagnetic compatibility and the return of high frequency disturbances through the grounding that actually disturb the AC-DC converter in the input of the grid. So I think that...
So what you're replying, it seems, I'm trying to summarize, is that actually the main reason for choosing a converter with isolation is not because of high power density or something, is because there is a problem with the protection and you want to disconnect the AC from the DC grounds, yes?
Indeed.
Okay, so that's is it a main constraint from the start of this thesis?
Yeah, it was one of the constraints that appeared in the course of the thesis. The first one,
because if you say it's a constraint from the start, when you write the manuscript, let's say you are writing the manuscript after thinking for 3 years, you say, okay, this is a constraint. I need isolation between low voltage AC and low voltage DC. So I need isolation. Yeah. So I'm not even thinking anymore about two-level voltage source converter or MMC. Then I don't need to write about it in my manuscript. So is it a strong constraint or it's something we can work around?
No, for sure, it's a strong constraint. And we can see the same type of choices being made all around the world. In China, they are using this type of isolated converters. In Europe, they also separate the grounding, the AC grounding from the DC grounding, sometimes using an LV transformer as well, using a two-level voltage source converter in the input instead of an isolated one. But everyone is making the same choices because the little experimental tests we have nowadays, all the communities observing the same type of phenomena that disturb the operation of the AC-DC converter if we do not have galvanic isolation.
Okay. So if you need isolation at the converter, then that's good, because at the same time you can win this, what you call the active short circuit capability, the fact that you can limit and open the circuit at the converter level, so that it solves the two problems. Okay. So if this is a clear requirement that you need to disconnect low voltage AC from low voltage DC, then you write it clearly, and then you can just discard more easily other topologies, as was discussed before.
Agreed.
So this slide works too, and it's a bit in the same direction. So here you are using a lot of protection device on the DC side to ensure the selectivity from the user to the substation. I'm wondering, you have a protection device right downstream the AC-DC converter.
This one?
This one, yes.
Mm-hmm.
But at the end, you chose a converter that is able to limit and open the circuit whenever you want, much faster than this protection device. You can really, so do you really need that device?
It is once again a very pertinent question. Indeed, if we are looking to the capability of the converter to completely shut down or to limit during a certain period of time, we do not actually need, but we decided to maintain these protection devices in the case the operation of the control system of the converter do not operate correctly in order to limit the short circuit current, meaning we would have an even higher short circuit, which means that for this case we could be selective with a fuse, or in specific scenarios with a thermomagnetic circuit breaker in this position.
Okay, so what I understand is that this is here, not really needed normally. It's only needed if the protection of the converter fails. Yeah. So I understand the point, but actually on this graph, you are missing that on the AC side, between the transformer and the converter, you have another DC circuit breaker, AC circuit breaker, which is conventional, that works well. And if the converter fails, it should be the AC circuit breaker that opens. So once again, do you really need this protection device?
I think what we tried to do was to guarantee a certain safety from the point of view of the converter. So if we have a short circuit larger than 60 amps, meaning that the converter is not able to saturate the current, and we can reach 70 or even 100, the proposition was to have a faster protection device in order to stop the short circuit, avoiding it to damage the AC to DC converter.
Okay, so it's here, actually not just to save the converter. In case it fails, you want to save the converter with this protection device. It's not really there for the grid protection. It's not really there for the selectivity, actually.
From a selectivity point of view, indeed, the control
system. The converter is doing it, the AC side is doing it, that's selectivity, but this one is not really there for selectivity. It's here if it fails to protect the converter. So it's kind of part of the converter at the end.
Yeah, it would, in cases that we were able to see equipment that came from manufacturers, we were able to see this type of ultra-fast fuse always connected in the output of the converter, but always making part of the converter.
Yeah, it's kind of inside the case of the converter. Okay.
Yes.
So in the same kind of discussion, do you need a fuse on the plus pole and minus pole, or only on one of them, and why?
So we decided to put 2 fuses because from the side of the protection regarding pole-to-pole faults, actually we only needed one, but as we are considering TNS grounding system and with a analysis to pole-to-ground faults, considering that it behaves exactly like a short circuit and a pole-to-pole fault, it would be interesting to protect both poles from pole-to-ground instead of only pole-to-pole. To protect pole-to-pole, only one is necessary. To protect from pole-to-ground, maybe there are two that are necessary if there is a residual voltage between negative pole and the TNS system, grounding system.
Okay, maybe simulation can help to make sure, but yeah.
For sure.
Okay, I understood. I have another tricky question for you. Open question still. It's about this nominal power of the converter. I see in your thesis is not the focus. You are kind of changing all the time between nominal power. And here for today you said 3.5 kilowatt. Why not? So my feeling is, wow, this is a lot of work, 3 years of work for only 3.5 kilowatt. So I'm asking again, is it the target nominal power for a real application like this of this converter? Yes or no? And if no, what will be the nominal power of this converter?
I think no. So to answer the first question, I think 3.5 it's too small. For even if we are talking about a little home grid, it's still too small. But I think for example, residential applications, what we can see in the literature are powers around 10 kilowatt in terms of power. And for commercial buildings, it varies a lot, mainly based to the size. And we were not able to reach the full potential here in terms of power, mainly because we were trying to avoid the destruction of the prototype during experimental tests.
But there is this question between prototype and the case study. So it's more for the case study. So let's say more than 20 kilowatt. Okay. So this is important. I have the feeling in the thesis because you are kind of in the thesis saying, okay, I'm going to study this system, monopolar, constant voltage. So you make a lot of decisions that you're trying to justify, good, but you never tell us what's the power of this system, and that's super important because actually you're comparing AC-DC converter topologies, and you're saying, I choose this one, but if you don't tell me the power, maybe a converter topology that you discarded should be included at another power level. So that's the main point. I don't know, if you're at 1 gigawatt, then, you don't think about DAB anymore. There is no way, So that's super important. If you tell me I'm going to do a 500 kilowatt DC grid with a DAB, I say good luck. It's possible, but like medium frequency transformer at that power level, it's, So that's super important to state what is your power level so that we can really justify better the choice of this converter and understand what is the range of application of this solution, this given solution. So maybe you can modify a bit in the thesis a bit later.
Thank you. Okay,
last words before giving back the microphone because I have a timing here. So at the end, what we see from all this work is that you propose a functional solution for this problem, which is an interface AC-DC converter between a public low voltage AC distribution grid and what you call internal low voltage DC distribution grid. So only this concept is very interesting from the discussion point of view. Just to put the right words is super interesting. You had a lot of discussion during the thesis about how am I going to call this converter, And for today you chose AC-DC interface converter, which I love. I think is the right word. But before you chose, I don't know, AFE or, I think. So the converter and the protection topology that you chose seems to work, seems to solve your problem. So that's a good thing. And I believe it's going to be a point of reference for other theses. In the future, we will have to consider this as a maybe base topology and compare other stuff to see if it's better than this one or not. So from my point of view, it's one of the first functional solutions that I see for this problem. So well done. Okay, that's really the originality of this thesis for me. So once again, I want to congratulate you on your report. That is very useful for the community, and we are going to have to read it again. I'm looking at Frédéric. I want to congratulate for the presentation that is clear, that clarified few points. So that's good. I'm super happy to be here today. And thank you again for inviting me.
Thank you very much, Mr. Caval.
Bien, merci. Le timing a bien été tenu, donc pas de problème. Je donne la parole par la suite au professeur Brahima Dakio.
Ok, merci Madame la Présidente. Donc moi je vais parler en français. Hein, pour le dialogue des cultures, ça va être bien.
Très bien.
En tout cas, merci de nous avoir fait part, en fait, proposé un exposé qui est très clair sur un travail qui lui-même est vraiment très très intéressant. Et bon, ce que je vais essayer d'apporter, enfin, c'est d'essayer d'échanger sur un certain nombre de points, hein, sur le concept même de protection par rapport à l'électronique de puissance. Alors, dans ce que vous nous avez présenté, au départ, dans le document écrit, hein, vous avez présenté les convertisseurs par fonction. Je trouve que c'est bien, mais le problème, c'est que vous allez travailler sur les transitoires. Et le transitoire de l'électronique de puissance, généralement, il est vraiment piloté par les grandeurs qu'on dit des grandeurs d'état. C'est-à-dire que quelque part, je ne peux pas faire n'importe quoi quand j'ai un courant dans une inductance et je ne peux pas faire n'importe quoi quand j'ai une tension au bord d'un condensateur. Voilà les principes de base de l'électronique de puissance. Maintenant, quand je veux protéger, alors d'ailleurs, au départ, quand on parle de protection, qu'est-ce qu'on protège? Dans tout ce que vous avez fait, quand je vois protection, qu'est-ce qu'on protège? Est-ce que vous pouvez me répondre là-dessus avant qu'on continue?
Alors, l'idée, c'est de pouvoir utiliser des différents dispositifs pour protéger les utilisateurs, c'est le principal. Après, le système, ça veut dire le système de distribution en soi, et les équipements qui sont connectés au réseau, mais principalement les utilisateurs.
Bon. Donc, la notion de protection des hommes, en fait, des utilisateurs, on va dire c'est nous, hein, parce que si c'est un robot, bon, peut-être on ne va pas le protéger de la même manière. Donc, il y a un problème là, ça dans votre manuscrit, ça a un peu manqué. C'est toutes les considérations qu'on peut avoir sur la protection des personnes vis-à-vis du courant continu.
Okay.
Ça manque parce que, bon, on est des techniciens, généralement on sait faire des choses, mais on oublie que, au final, c'est l'homme qui va utiliser ça, où les gens vont être en contact avec le matériel, et d'ailleurs, la haute tension et la basse tension, même en alternatif, en fait, il y a beaucoup de règles qui sont liées tout simplement à la protection des gens.
Tout à fait.
Donc, déjà, c'est de dire, alors, donc, si je reprends votre travail, au niveau des topologies des convertisseurs, bon, vous avez dit, on prend le courant continu. Vous avez commencé par montrer, et c'est vraiment très bien, j'ai apprécié, les deux types de conversion alternative continue qui sont fondamentaux pour l'électronique de puissance. C'est un convertisseur avec une commutation de courant et puis un convertisseur à onduleur de tension. C'est les deux. Il n'y en a pas 36. Hein. Fondamentalement, quand on regarde, il n'y a que ces deux-là. Et vous avez fini par choisir les convertisseurs à onduleur de tension. Est-ce que vous pouvez m'expliquer véritablement pourquoi dans une basse tension, on n'utiliserait pas des convertisseurs à commutation de courant?
Par rapport à la connaissance que j'ai, normalement, ces types de convertisseurs à commutation de courant, ils fonctionnent avec je pense qu'aujourd'hui, des thyristors. Et donc, ils marchent très bien pour des réseaux qui ont une très forte puissance de court-circuit, ce qui n'est pas le cas dans notre étude, sachant qu'on étudiait de petits réseaux de distribution, soit résidentiels, soit pour d'autres types de bâtiments. Donc, et aussi, dans notre cas, ça serait plus simple d'utiliser ces types de convertisseurs pour exploiter, maintenant on n'a pas implémenté encore, mais la bidirectionnalité de flux de puissance. Et voilà un peu les raisons.
Vous savez qu'avec le convertisseur à commutation de courant, ben, vous avez dit la bidirectionnalité. On a un souci, c'est qu'avec ça, il faut inverser les tensions. C'est-à-dire que votre bus, normalement continu, va être à tension bidirectionnelle. Pour inverser, alors qu'avec le convertisseur à tension, c'est le courant. Vous changez le sens du courant. Donc c'est ça qui fait que ben, finalement, dans l'application, c'est quand même un peu difficile d'aller mettre dans du continu, un peu chez l'habitant, on va dire ça comme ça, hein, avec une tension qui change de sens tout le temps. Bon, donc ça, j'ai vraiment bien apprécié au départ ce que vous avez présenté. Mais une fois qu'on arrive à la protection, si on utilise, alors ce schéma-là, il est très intéressant. Là, vous voyez, vous avez plusieurs branches, vous distribuez finalement de l'énergie. Donc, chaque convertisseur va amener sa caractéristique propre. Donc, vous avez là, et vous l'avez bien dit, vous avez créé un point d'interaction. Donc, point d'interaction. Pendant que je suis en train d'essayer de regarder d'un côté, il y a d'autres éléments qui influencent mon point de couplage. Alors, dans votre cas, je ne sais plus, on va prendre là où vous avez fait le schéma des protections avec le court-circuit.
Et les courbes de sélection.
Non, juste le schéma avec les espèces d'éclairs que vous avez mis là. Voilà, par exemple là. Hein. Bon, ce n'est pas exactement mais le schéma du dessus. Vous dites, là, j'ai un court-circuit en sortie, 4 et 5. Bon. Le problème, c'est que ces 4 et 5, ce n'est pas ce convertisseur seul qui pilote ce qui va se passer à cet endroit. Il y a tout ce qui est connecté par ailleurs qui va interagir. Donc, le convertisseur qui est là, même si j'essaye de le contrôler, il ne contrôle pas tous les phénomènes qui arrivent. Alors, qu'est-ce que vous pensez de ça? Comment vous réglez ce problème? Parce que le convertisseur, si vous faites en sorte qu'il participe, sa participation est de toute façon limitée. Et donc, les autres interagissent. Et cette interaction, si vous ne la connaissez pas, vous ne savez pas comment dimensionner le système de protection.
Tout à fait. Je pense que par rapport aux autres éléments qui peuvent être connectés, ceux qui peuvent avoir une importance plus grande par rapport à justement contrôler les courants qui passent quand on a un défaut, ça serait des batteries ou des panneaux photovoltaïques, en considérant que tous les charges sont protégées par des disjoncteurs de type thermomagnétique d'une façon similaire à ce qu'on a en AC. Et pour ça, c'est vrai que j'ai pas beaucoup abordé le sujet dans le manuscrit, mais ce sont des choses qu'on regarde un peu de notre côté, que ce soit pour des micro-réseaux DC ou pour des micro-réseaux en AC. Et je pense que c'est vraiment important de les prendre en considération et d'utiliser, par exemple, pour éviter cette contribution de ces types d'usages PV et batterie, des protections de type anti-islanding, de protection de découplage plutôt, pour éviter justement ces types de contributions, pour qu'on puisse maîtriser vraiment le comportement du court-circuit de notre côté.
Oui, bon, en fait, c'est très difficile parce que dans la configuration, bon, vous avez parlé, bon, je crois qu'avec Manuela, on travaille beaucoup sur ces aspects-là. Quand vous avez un bus comme ça, bien souvent, un des intérêts, c'est qu'on peut injecter des énergies de sources diverses sur ce point-là, parce que bon, c'est un point à fréquence nulle. Ça permet ensuite de gérer les différentes fréquences et les différentes possibilités d'injection. Mais quand je crée un bus continu comme ceci, parce que finalement, comme plusieurs équipements vont se coupler là-dessus, c'est un bus continu. D'accord ? Quand je crée un bus continu, alors vous avez votre boucle de régulation. Vous pouvez revenir là-dessus. Vous avez présenté un convertisseur avec un module genre PLL en entrée.
Est-ce que c'est celui-là?
Est-ce que ça... Non, non, c'est pas ça. Allez-y encore, là. Revenez sur le module d'entrée. Vous avez mis...
c'est celui-là, peut-être?
Vous avez un bloc. J'ai pas noté, malheureusement.
J'essaie de revenir.
Revenez.
Peut-être que c'est celui-là. Alors, non?
Voilà,
un peu,
celui-ci.
ouais.
Celui-ci. Bon, alors là, vous avez un petit souci parce que le point de couplage, c'est-à-dire la sortie DC, vous avez un convertisseur que vous utilisez pour contrôler l'entrée et la sortie. D'accord? Bon, vous savez que ça, en fait, vous ne pouvez pas. Donc vous allez contrôler quelque chose bien et l'autre n'est qu'une conséquence du contrôle que vous faites sur le premier.
Tout à fait.
Donc en sortie ici, en fait, la tension, puisque vous faites de la régulation de courant en entrée, notamment en forme pour avoir une absorption un peu sinusoïdale, hein, il ne faut pas perturber. Donc la tension de sortie n'est pas véritablement contrôlée, puisqu'elle sert simplement à contrôler le courant d'entrée. Vous voyez? Et elle est une conséquence du transit d'énergie. Donc ce n'est pas la tension qu'on contrôle. Donc quelque part, si je mets cette sortie de tension avec d'autres éléments, est-ce que vous pensez que je vais pouvoir contrôler ce niveau de couplage là convenablement? Donc il y a un problème à ce niveau-là. Hein? Je ne sais pas si vous voyez vraiment, parce que la plupart du temps, alors j'en viens avec l'idée qui est sous-entendue, quand je veux connecter un autre élément ou d'autres éléments à ce point, j'ai intérêt à ce que ces éléments n'interviennent que sur le courant et non la tension. Puisque la tension va être contrôlée, mais le courant, lui, les autres éléments, ce sont les éléments perturbateurs, c'est les courants des autres éléments. Donc là, vous avez un problème de niveau de tension, de contrôle. Quand vous allez mettre plusieurs éléments, ça va être un peu difficile. Vous comprenez ce que je veux dire? Donc ça, c'est la régulation générale. Bon. Alors, vraiment très intéressant aussi. Alors, si je m'en tiens à cet aspect-là, vous avez donné dans votre document écrit, mais c'est vraiment des discussions, hein, le travail est très intéressant. Dans le document écrit, vous avez montré une courbe dans laquelle vous avez, c'est une flèche comme ça, là, vous avez 3 zones. La zone où vous avez la tension de référence, et puis vous avez une zone où la tension est plus grande, et puis une zone où la tension est plus faible. Bon, vous ne l'avez pas montré ici, mais c'est une courbe qui est dans le... Et là-dedans, ce qui m'a paru curieux, vous avez dit que quand la tension augmente, c'est là où on demande la plus grande puissance. Vous voyez?
De consommation, oui, effectivement.
Oui. Alors que pour moi, c'est le contraire. C'est-à-dire le point de couplage, sa tension augmente quand je décharge. Quand je demande moins de puissance, c'est là où la tension augmente. Quand je demande plus de puissance, la tension a tendance à baisser.
Je comprends.
Voilà.
Gros, je pense que ce que j'ai voulu considérer, c'est un réseau où, par exemple, on a des batteries et du PV. Et imaginons que le PV, il est capable de produire parce qu'il y a beaucoup de soleil.
Oui.
Voilà. Donc, il est capable de produire et d'injecter plus de courant dans le bus. Donc là, la tension va monter. Et c'est là où on peut dire aux charges, si on a le contrôle, utiliser de la puissance, genre augmenter recharge de véhicule ou autre chose.
Alors, d'accord. Donc, moi, je pense qu'il faut corriger cette partie-là, parce que vous venez de dire que la tension augmente quand j'injecte, pas quand je consomme. Alors que dans le texte, vous avez dit que c'est quand je consomme que ça augmente. Alors que c'est la période plus favorable pour consommer, c'est ce que vous voulez dire.
Tout à fait.
Mais bon, c'est mal dit, hein,
okay.
dans le document. Voilà, bon, donc ça, c'est les aspects. Alors, dernier aspect, en échange là-dessus, parce que bon, j'ai ça sous les yeux. Effectivement, bon, au départ, vous avez présenté les options, hein, qui s'offrent à nous, là, pour éventuellement optimiser l'alimentation de plusieurs charges. Et vous avez dit, avec ce schéma-là, on voit bien qu'au-dessus, on a une cascade de convertisseurs, et en bas, évidemment, on a le convertisseur final. Et bien souvent, ce convertisseur final, il est du type DC-DC. D'accord ? Mais quand on regarde cette courbe, on se dit, et ça rejoint un peu la remarque la dernière remarque, là, je ne sais pas si c'est vous ou c'est notre collègue ici, vous avez un point intermédiaire, finalement, continu, là. Et vous avez des ACDC. voilà, en haut. D'accord?
Là,
Donc j'ai du
ouais.
AC, voilà, et j'ai un point intermédiaire qui est du DC. Qu'est-ce qui m'empêche de relier tout ça et de faire, finalement, ma distribution, c'est toujours AC, mais c'est au point final que je fais juste la transformation AC-DC.
De relier, par exemple, ces points qu'on voit ici, un petit orange là, par exemple.
Oui.
C'est effectivement possible. Et il y a même plusieurs études qui proposent ces types d'approach, ces types de solutions. Le seul possible inconvénient, c'est que pour faire ça, on allait avoir besoin, pour la majorité des applications, en considérant les charges électroniques, ordinateur ou portable par exemple, ça serait de réduire la tension. Du coup, on perd un peu en efficacité, potentiellement, on perd un peu en efficacité énergétique. Mais voilà, c'est entièrement souhaitable sur plusieurs scénarios, par exemple.
En fait, bon, il y a quand même, je pense qu'il y a autre chose aussi, c'est que quand on fait ça, on est, à mon avis, on a un degré de liberté en termes d'adaptabilité. Mais si vous mettez justement la seconde solution, elle est intéressante, elle paraît intéressante, mais au départ, elle contraint tout le monde à travailler à partir de la même tension continue.
C'est vrai.
Et ça c'est ma dernière remarque, c'est quand vous faites des convertisseurs, vous avez dit, vous travaillez à 40 kHz, d'accord, pour réguler tout. Votre problème, c'est qu'à un moment donné, c'est les capacités de commutation de l'électronique de puissance. Alors, vous avez le rapport cyclique. Donc, quand vous montez en fréquence, vous avez un rapport cyclique, une variation de rapport cyclique qui se trouve limitée. Donc, vous ne pouvez pas régler avec finesse l'ensemble des grandeurs que vous contrôlez. Donc, vous voyez, avec les DC, on manque de souplesse, cette souplesse qu'on a avec l'AC, puisqu'il y a un seul paramètre finalement qu'on règle, c'est le rapport de transformation. Et donc, il y a certains de nos collègues, notamment ceux de Danemark, là, avec, comment il s'appelle? Oui, Albor. Eh bien, ils sont allés sur le concept d'électronique vu comme des transformateurs. Parce que le souci, c'est cette adaptabilité qui est nécessaire. C'est-à-dire que la courbe, le schéma du bas, idéalement, c'est intéressant, mais fonctionnellement, ça pose un souci en exploitation. Si on ne va pas jusqu'à la notion de module qui fonctionne comme des transformateurs, puisqu'on a besoin de cette variabilité de paramètres pour que les applications soient satisfaites. Voyez. Donc ça, c'est un peu, c'est vraiment la discussion ouverte. Hein. Ce que vous avez fait, c'est vraiment très intéressant et ça positionne d'un côté ce qu'on peut envisager, mais il faut aller plus loin encore sur ces aspects-là. En tout cas, félicitations pour votre travail, hein, qui est vraiment très très intéressant, parce que bon, vous avez eu beaucoup de, beaucoup de littérature, hein, que vous avez trouvé, mais moi je ne m'étais jamais intéressé au problème à ce niveau-là, hein, jusqu'à ce point, et c'est vraiment très intéressant. C'est un document qui est très intéressant. Donc pour finir, je vais remercier mes collègues de SIA qui m'ont invité, hein, et donc j'étais très heureux de participer à l'évaluation de ce travail. Merci.
Merci beaucoup, Monsieur Dacchio.
Bien, merci, professeur Dacchio. Je donne la parole par la suite à Dr Yang Xavier, si vous voulez dire quelques remarques, questions courtes, s'il vous plaît.
Merci beaucoup, Madame la Présidente. Voilà, je suis un peu juillet parti, comme j'ai participé à ce travail. J'ai juste une petite recommandation. Ton travail sur la qualité de l'électricité, par exemple, tu as réussi de mesurer par essais et simulation de l'impédance, régime permanent fréquentiel. C'est très utile pour utilité pour opérateurs de réseau parce qu'on veut estimer la qualité de l'électricité de niveau lors de futures conversions de clients. C'est très intéressant. Et merci beaucoup. Et pour ton futur travail, je pense il faudrait étudier comment mesurer l'impédance dynamique d'un convertisseur statique. Ça peut être utile pour la qualité d'électricité en régime transitoire et voire protection. Donc, ce sera vraiment intéressant. Pour finir, j'appréciais ta qualité de travail itérative et dynamique entre simulation temporelle fréquentielle et retourner au labo, réparer le montage. Voilà, ça, c'est vraiment une qualité très, très utile pour ton futur travail. Merci beaucoup.
Merci beaucoup, Monsieur Yang.
Bien, merci. Avant de donner la parole à vos encadrants, le directeur de thèse et le co-encadrant, je souhaiterais également, en tant qu'examinatrice, non seulement comme présidente, exprimer quelques remarques. Donc tout d'abord, je m'associe à mes collègues pour vous féliciter pour votre soutenance, qui a été vraiment une présentation de très bonne facture et dynamique, et sur des slides avec vraiment de très bonne facture. Puisqu'on est là sur la slide 8, donc c'est là d'un coup, quand je vois comment vous projetez par rapport à cette distribution en courant continu, dont il est vrai, les débats en Europe sont arrivés un peu plus tard, et notamment en France, mais ailleurs, c'est depuis 2005-2006 assez débattu. Et tout part de photovoltaïque, car l'idée, c'est de se dire, si je fais vraiment de la production propre dans mon bâtiment, alors je peux avoir une meilleure performance. Mais selon vous, devrais-je appliquer ce concept de LVDC à tout bâtiment ou uniquement à des bâtiments qui font aussi une auto-alimentation par de photovoltaïque?
Alors, par rapport aux données que j'ai trouvées dans la littérature, l'utilisation du courant continu pour ces types de distribution interne au bâtiment, que ce soit résidence ou des bâtiments commerciaux, on a la possibilité d'avoir un gain considérable en efficacité si effectivement on a de la génération ou de l'autoconsommation, comme on appelle. Si on n'a pas cette possibilité, les gains en efficacité, pour l'instant, peut-être qu'ils ne se justifient pas, parce qu'ils sont très petits.
Oui, je le confirme. Est-ce que vous pourriez mettre maintenant la slide 23 qui était avant, s'il vous plaît?
Avec plaisir.
Donc là, j'ai juste deux petites questions rapides. Vous n'avez rien dit de clair. Bon, dans le manuscrit, c'est dit que c'est écrit, c'est tiré de la littérature, mais vous avez choisi une tension de bus à 350 volts. Pourquoi?
Il y a plusieurs raisons. Effectivement, ça fait partie de mon premier étude bibliographique, car en n'est pas connaissant la tension d'exploitation, il était compliqué de choisir tous les autres aspects de la recherche. Mais ce que je peux dire, c'est que le 350, tout d'abord, il a été commencé à être standardisé de façon vraiment au début, un peu par deux types d'organisations différentes en Europe, mais aussi il représente un bon niveau de compatibilité entre un bon compromis entre l'efficacité et la capacité de protéger le système. Parce que par exemple, aujourd'hui, si on cherche des dispositifs de protection qui fonctionnent en DC à une tension beaucoup plus élevée que ça, ils n'existent pas dans le marché.
Oui, je peux être d'accord en partie avec ce que vous venez de dire. En fait, je ne suis pas allée pour lire vraiment les standards. Je ne savais pas qu'il y a vraiment des standards pour les 350, mais à l'origine, puisque moi-même j'en ai fait des travaux là-dessus, c'est effectivement la valeur que vous obtenez si vous voulez utiliser l'infrastructure existante de réseau électrique, d'une installation électrique d'un bâtiment, faire le même transfert de puissance avec le moins de pertes, et donc vous passez un peu aussi par le facteur de puissance, et donc vous tombez à 350 et maximum 380. C'est de là que ça vient, cette valeur, effectivement. Ensuite, j'imagine que l'exemple de 48 volts, bon, c'est juste comme ça un exemple,
En gros,
parce que ça veut rien dire.
ça vient un peu de la possibilité d'utiliser le USB-C, la version un peu plus puissante.
Oui, mais là, vous avez une diversité de valeurs de tension et tous les appareils, ce qu'ils acceptent en interne comme valeur de tension, tout est très, très divers et donc manque de standardisation en quelque sorte. OK. Autre chose, ce que je voulais souligner, je rejoins tout à fait ce que le professeur Andacchio vous a dit précédemment. Et je rajouterai, évidemment, vous avez besoin de contrôler la stabilité du bus d'essai. Si vous ne contrôlez pas ça, si vous pensez que vous le faites en faisant la boucle de contrôle de votre convertisseur, alors là, c'est raté. Certes, c'est un problème qui déborde un peu par rapport au sujet de votre thèse, mais ça vaut la peine de le mentionner si vous voulez vraiment donner vos perspectives de tout ce qui est sur le LVDC en termes d'approche globale. Ça, vraiment, le contrôle de bus d'essai est essentiel, puisque là, le PV, le stockage, bon, je pense que vous ne savez pas vraiment comment ça fonctionne, mais vous avez besoin d'un contrôle, savoir ce que vous faites s'il n'y a pas assez de PV ou s'il y a un PV annexé, qu'est-ce que vous faites de votre stockage, vous le faites intervenir ou non, et quand vous allez voir les pics de tension sur votre bus, vous allez bien comprendre qu'on a besoin de faire de la très bonne stabilité. Sinon, déjà, vos convertisseurs vont souffrir parce que de 350 à 48, l'efficacité va baisser. Si de plus, vous faites subir toutes les pics, là, on est dans des complications. Donc là, effectivement, retenez, c'est essentiel. Vous êtes typiquement dans un microgrid d'essai. Vous avez besoin de contrôler la stabilité de bus. Et ma dernière petite question, vos publications sont plutôt dans des conférences?
Oui.
Avez-vous l'intention de valider votre thèse, ce qu'on dit, valider la thèse avec un article de revue?
Tout à fait. Alors, à très court terme, on est en train de préparer un article de revue qui concerne plutôt la partie liée à l'état de l'art, autour du décès, dans une perspective d'utilisation pour les réseaux de distribution. Et un peu plus tard, on aimerait aussi soumettre un autre article de journal où on aborde plutôt la partie liée à la stratégie des protections et comment on peut être sélectif en décès au plus faible coût possible.
Ok, je vous remercie. Bien, donc là on arrive à la fin et je donne la parole à vos encadrants, le directeur de thèse, Octavien Courin.
Merci beaucoup, Madame la Présidente.
Merci Madame la Présidente. Je tiens à remercier à tous les membres du jury pour être là. C'est un vrai plaisir de vous avoir à côté de nous. Donc, il y a eu beaucoup de discussions autour du travail de César. Moi, bien sûr, je ne vais pas poser des questions. Donc, je l'ai encadré, donc c'est pas... Voilà. Mais je tiens à spécifier qu'en tant que thésard, tout s'est très bien passé. Donc, il était autonome, il a beaucoup bossé. Il y a beaucoup de choses qui n'ont pas été dites pendant la présentation, mais sur lesquelles il a travaillé. Juste pour donner un exemple, il a brièvement parlé des DSP, mais en fait, c'était un travail vraiment très conséquent parce qu'il fallait arriver à faire les calculs suffisamment rapides pour que la boucle de courant réagisse correctement. Donc, c'est pour ça qu'on est parti sur le DSP avec multiplicateur hardware et toutes les options. Donc, c'est en fait, effectivement, on peut pas tout montrer, on peut pas tout expliquer, mais il y a un travail assez conséquent. Après, c'était une thèse chiffre, Donc, on a dû aussi jongler avec les demandes des entreprises, surtout qu'il y avait deux entreprises impliquées, donc EDF et Enedis. Donc, c'était pas forcément évident en permanence. Et sur le prototype, en fait, étant un chiffre, on a décidé 50% laboratoire, 50% en entreprise. Du fait de l'éloignement, on a décidé de commencer avec le laboratoire. Donc, c'est pour ça que nous avons essayé de mettre en place très rapidement le prototype pour qu'il puisse partir à Paris dans l'entreprise avec un prototype fonctionnel. Donc, il y a eu beaucoup de contraintes qui nous ont fait partir sur certains choix et qui sont... C'est pas la place de toutes les expliquer. Mais je tiens encore à remercier César pour son implication. Je tiens à remercier aussi Enedis pour la possibilité qu'ils nous ont donné d'intervenir sur cette thèse. Et juste, je tiens à spécifier que César il va signer son contrat lundi avec EDF. Donc, voilà. C'est une reconnaissance de plus, à mon avis, pour la qualité du travail. Et le travail, bien sûr, il ne va pas s'arrêter. Donc, on va continuer à travailler là-dessus. Merci beaucoup.
Bien, merci. Je donne quand même la parole au co-encadrant, donc à M. Alvaro Larrea-Leal.
Bon, merci Madame la Présidente pour cette opportunité. Et bon, j'ai joint les remerciements d'Octavien, membre du jury, à EDF, à César, surtout félicitations, parabéns par ces jolis travaux, énormes travaux que tu as fournis. On ne va pas insister là-dessus. Les difficultés rencontrées, partie software, partie hardware, voilà. Ce que tu as pu faire, c'est bel état de l'art. Des choses qui restent encore à faire, c'est sûr, mais bon, les travaux, c'est énorme, de mon point de vue. Et surtout, voilà, c'était un vrai plaisir de travailler avec toi, franchement, par ta curiosité, tes qualités scientifiques, techniques, mais aussi personnelles. Donc, franchement, encore une fois, félicitations.
Merci beaucoup.
Bien, merci. Avant de se retirer, je suis dans l'obligation de demander, y a-t-il un docteur dans la salle qui souhaiterait poser une question ou faire une remarque, s'il vous plaît? Bien. Bon, le jury va se retirer et nous retrouverons 30-40 minutes après. Merci.
Merci beaucoup à tous.
Bien, Monsieur César Augusto SLONGO, le jury s'est réuni et donc a délibéré. On considère que vous avez fait une présentation claire, dynamique et synthétique de vos travaux. Vous êtes appuyé sur des supports d'excellentes factures et on a apprécié la maîtrise de la langue anglaise et que vous avez bien répondu aux questions en français et en anglais. Donc vous avez témoigné de réelles qualités pédagogiques et vous avez réussi à mettre en avant de façon claire les différentes contributions à la conception d'un réseau LVDC, c'est-à-dire le convertisseur, la qualité de l'énergie et les protections spécifiques. Donc le jury a souligné la qualité et la quantité de travail réalisé et les compétences que vous avez mis en œuvre, modélisation, conception et également implémentation expérimentale. Au cours de la discussion, on vous a posé beaucoup de questions. Vous avez répondu avec assurance et pertinence et vous avez confirmé l'expertise et votre hauteur de vue dans votre domaine, ainsi que votre capacité à mener des travaux de recherche selon une démarche rigoureuse. Donc, pour toutes ces raisons, le jury unanime vous propose au grade de docteur de l'Université de Bordeaux, spécialité électronique. Je vous félicite.
Merci beaucoup. Oui, j'aimerais bien remercier les trois grandes parties des personnes qui ont fait partie de tout mon projet de fin de recherche qui a abouti à la fin de cette thèse. Donc, au début, j'aimerais remercier ma famille, qui est là présente et représentée par ma fiancée Laura Meyer. Sans elle, ça serait certainement pas possible d'être là aujourd'hui. Un deuxième, j'aimerais remercier mon équipe d'encadrement, donc Octavian, Alvaro, Xavier et Boris qui est là aussi. Sans vous, encore une fois, ça ne serait pas possible. C'était un énorme plaisir de pouvoir mener ces travaux avec vous et j'aimerais vous remercier encore une fois pour tout ce que vous m'avez appris et pour faire une partie importante de mon parcours académique et de mon parcours sur l'industrie. Et un dernier, j'aimerais remercier tous mes collègues doctorants et tous mes amis d'être là. Vous avez fait partie des points, des challenges de cette partie plutôt et des côtés positifs aussi. Donc merci beaucoup d'avoir participé de cette étape de ma vie. Sans vous, encore une fois, je ne serais pas là aujourd'hui. Donc merci beaucoup à tous.
Donc, maintenant, après cette soutenance et cette décision d'admission, de proposition au grade de docteur, on vous demande, si vous êtes d'accord, de prêter serment par rapport à l'éthique scientifique pour toutes vos recherches, pour toute votre vie. Donc, je vous invite à lire le texte ici présent. Donc, voilà.
Merci. Donc, en présence de mes pairs, parvenu à l'issue de mon doctorat en électronique et en ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quels qu'en soient les secteurs ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Bien, merci. Et on vous félicite, vous êtes un chercheur.
Merci beaucoup.
Qui a prêté serment. Voilà.
Merci beaucoup, Madame César.
Je récupère mon papier.
Très bien.
Merci.
Merci. Merci beaucoup, Monsieur Keval. Avec plaisir. Merci beaucoup. Merci beaucoup, Tavi. Merci beaucoup, Alvaro. C'était un plaisir. Merci, Xavier. Également, c'était un plaisir.